Traditionally, we divide chemistry into inorganic and organic categories. However, this division only makes sense for educational purposes today. Chemistry is a unified field, with its third pillar being physical chemistry, which is indispensable for modern chemistry. For chemical synthesis, where new substances are created, it's crucial to determine their structure. In this regard, nuclear magnetic resonance spectroscopy, internationally known as NMR, is an invaluable tool. Although the discovery of nuclear magnetic resonance was a result of physics, today we consider NMR a method of physical chemistry for determining the structure of substances, one that does not distinguish between inorganic and organic chemistry. By the way, NMR is associated with 3 Nobel Prizes awarded in 1952, 1991, and 2002. The last of these was granted for the expansion of NMR methodology to study biomicromolecules. At the Faculty of Science of UJEP, a dual NMR spectrometer was put into operation at the end of 2020. The central part of the instrument is the superconducting magnet connected to the radiofrequency unit, the so-called console. By a series of cables, the probe into which the sample is loaded on a rotor in an NMR tube is inserted from below and is automatically tunable. The operator controls the spectrometer from a workstation. The instrument is equipped with a robot for programmable sample exchange with 32 positions. The scope of NMR spectroscopy can be documented on the periodic table of elements. Only 4 elements in the periodic table lack an MR-active isotope or are radioactive. Several others have both MR-active and inactive isotopes. From a chemical perspective, it's essential to note that the most abundant carbon and oxygen isotopes are not NMR-active, while the hydrogen isotope 1H is NMR-active. Now, let's demonstrate the importance of NMR spectroscopy in solving the structure of a reaction product. The transmetallation reaction that produces a rhodium complex with a cyclopentadienyl ligand and another ligand, an N-heterocyclic carbene with a polyfluoroalkyl. Substituent known as a tag is shown in the scheme. The size of the product molecule is better illustrated by the rotating model. The compound contains carbon, hydrogen, fluorine, silicon, nitrogen, rhodium, and chlorine elements. While spectra of all these elements can be measured, we only needed the first 4 to determine the structure. So-called one-dimensional spectra of hydrogen 1H, carbon-13C isotope, and heteronuclei 19F and 29C confirm the structure of the reaction product. Additional confirmation can be obtained from 2-dimensional spectra, which correlate spectra of the same or different nuclei. The studied substance was measured in a deuterated solvent, which is, in NMR terminology, in the liquid phase. Our spectrometer is also equipped to measure spectra in the solid phase. You can see the filling of a special ceramic vial, which the same robot, used for the liquid phase, can introduce into the NMR spectrometer after the probe is changed.